Hello guys, today I will show you, in fact I will teach you how I created this effect. What makes this effect so special is that it kind of curves as you move and shrinks as you move in the opposite direction. It can be super useful for thrusters, jets, tentacles, anything your imagination can think of. In fact, let us take a look from below and observe the effect. So without further ado, let's get excited and I'll show you right away. Alright, so let's get started. First, let's create a Niagara system. Empty. Niagara system jet trail. Then also create a material for the trail itself and call it trail. Open up the Niagara system. Add a ribbon render and remove this one. There you go. Open up the material, add in a particle color, connect it to the emissive, set it to translucent and lit, save. Alright. Oh, and in the particle state, disable kill particles when lifetime has elapsed, and in the emitter update, add a spawn per unit and set the spacing to 0.2 or voila. Now the problem is that our ribbon has an infinite lifetime and is not gonna remove the particles that are exceeding a certain distance. So let's get into this stuff. First of all, at particle spawn we want to create a new parameter value called current distance, and we want to feed in the distance at which the emitter was found at that current time frame. So if you go to emitter states, you can find distance traveled. So what we want to do is drag this in there, and there you go, you got the current distance. Now let's create a new sketch pad, drag this out of the way, and then we want to feed in the emitter distance traveled and our current distance. Sorry, this one is an old one, and subtract it to find the distance, of course. Now we want to create the parameter length and feed it in our module. So add in a float and call this in length, and then we want to check if this value is greater than our given length, and if that's true, then set alive to be false. So of course we're gonna have to invert this boolean. There you go. Now apply and then drag in the parameter. Of course we don't have the value is set to 0, so let's just say 100 perhaps, I'm not too sure. There you go. So now we are able to calculate the value going from 0 to 1 and use this as an index to sample a curve to set the ribbon scale and to create this nice curving effect. So let's get started. Go to our sketch module, create a new float and call this radius. Now if you take, if you divide this value by length, then you're gonna have a value going from 0 to 1. Now make sure to clamp it so it stays within 0 and 1 ranges. And now set a new float parameter, call it index over distance. And of course this should not be a module local, but instead it should be a particle attribute. Voila. Now create a map get, take our index, and then also create a new curve for float, call this in curve ribbon width. Now sample the curve and multiply this by our radius parameter, so call this in radius, add in a map set, connect it to the output module node, and set the ribbon width. There you go. Now pick a curve and set the radius value to be 10 maybe. Et voila. This index is gonna be very useful for us, and you'll see how much more stuff we can do with this. Now connect our trail to this imaginary jet, I will say. There you go. Point it out with the x-axis, and z should be up. There you go. Now ribbon renderer should be set to tube, and the radius, we can set this to 50 maybe. Now as we drag this around, we are spawning our jet's trail. But the problem is that as you move back, it kind of clips with the mesh, and this is something we really don't want. So how do we fix this? Well, we are gonna have to make the source, the start, to be stiff, and then the rest should become dynamic. So let's first make the whole trail stiff. So add in the parameter get, take the system forward axis, take our index, take our length, and also take the simulation position. So now multiply the forward with the index and the length, so now we are arranging the particles in a straight line, and then also add simulation position and the result so that it stays related, because our system is not set to local space, and of course we have not set it to local space because else it would also take rotations, and we don't want that. So add in a parameter set, set position, apply, and there you go. So now we want to interpolate the current stiff result with the actual spawn position. Now, of course, we are overriding the position, so let us first store the spawn position. So go back to the system overview, add particle spawn. In the set parameter, we want to create a new vector. In fact, let us do it the other way around. Let us first remove this input. Instead, say duplicate to namespace with modifier initial. Now drag this into the set parameter in our spawn update and set it to particle position. So now we have stored the initial spawn position, and in this sketch module the positions are being arranged into this straight line. So all we want to do is interpolate back to initial position. So let's go back to our sketchpad, make some space, another parameter get, and in this one we want to take our index of our distance, we want to take our erased positions, and we want to take our initial position, but we also want to sample from a curve, so we can adjust this index. So first let us sample from the curve, and then lerp our position with our initial position, and now say map set and set our position and there you go. Of course, we forgot to set our curve again. So there you go. Now it's staying stiff and it's becoming dynamic in the end. But we still got clipping going on. So what we want to do is take the device, create or find the velocity of the emitter as it travels. As you see now, it's traveling. And if it travels backwards, or if it's becoming idle, then lure back to the straight arranged line, basically. So now we want to find the emitter's velocity. So let's go back to our system overview, and we want to create a few attributes and parameters. So first, float called device velocity, a value going from 0 to 1. Another vector attribute called last position, to store the last position between frames to find the velocity. And then also two more float parameters, one called velocity accelerate, and one float called velocity slowdown. Alright. We want to set last position to be equal to the simulation position at spawn frame, because else we're gonna, in this first frame, we're gonna have a sudden very high velocity, which we don't want. Now create a new module called device velocity effect. Let us also change the name for this one and call this one set trail. No, you can't be for real. Oh my god. Oh, hey. It real sometimes. Now, velocity. in our map get, take the simulation position. It could also be the engine. Sorry, you can also use this one, but they're gonna be the same, so it doesn't matter. Now, take our last position, and that's no, that's not it for now. We also want the device velocity. To find the velocity vector, we just want to subtract last pos from the current position, and find and calculate the length for that vector. And then we want to multiply this with the accelerate, so create a float in accelerate, like so, and add it with the current device velocity. So it's gonna be a bit too messy, but we'll figure our way out. And now set device velocity. So as it travels, it's gonna calculate velocity, and it's gonna add it to the current velocity using the accelerate. So now we also want a slowdown. So again, some space. Let get, drag in the device velocity. In this one we also want the delta time. So why for the slowdown and delta time, and for the acceleration part not? Well, the acceleration part between frames is always gonna rescale, like the velocity is already kind of adjusted to the frame in between, but the slowdown not. So therefore we want to multiply the slowdown with delta time, if you understand. So in float, and call this in velocity slowdown. Voila. Multiply this, subtract, and subtract. So we want to subtract with the slowdown value. And now we want to clamp the float between 0 and 1, because here it's incrementing above 1, but we don't want to clamp it already here before, because the slowdown is gonna force it to never be able to fully reach 1. So it's okay that it exceeds 1, as long after here it's doing the slowdown and then clamping the velocity. So we can just copy over this one. Up. Up. Voila. And now let us use this velocity. So first of all, another float parameter called length idle. And we want to interpolate between these two using the velocity. So let's go to our set trail, and at the very start create a map set, we are gonna have to rewire some nodes, so bear with me, and then a map get. In our map get, take the in length and also take the in length idle. But also what we want is the device velocity. and lerp those. So if velocity is 1, then take the longer length, and if 0, then take the smaller length. And set this value and name it current, or no, let's call it interpolated length. Now instead we want to use this interpolated length, so rewire, remove pin, and there is another part where I was using length. Again, I hold Control and then drag it, and then again remove it. And before we continue, we want to set our parameters. So in our set trail length idle, there you go. And in our device velocity, we want to connect accelerate and slow down with the corresponding input values. Now go back to our scene, and we have got to first set our parameters. So length idle, maybe half of what the actual length. Slow down perhaps 3, and accelerate maybe 0.3. I don't know. Let's give it a try. It should be slowing down a lot more than that. So I took a quick moment to figure out the issue, and in fact there were two issues. One of which was the last position was not being set between frames, only at spawn. And then the second issue was that the velocity that we are getting between frames can be a very, very small decimal value. And again, I was multiplying this with another decimal value, which was giving me inaccurate results. So instead, we want to divide it. And now you gotta see acceleration as in range. So the greater the value, so imagine 500, the slower it's gonna accelerate. So if it's 10, then it's gonna be divided, and it's gonna still be a greater value, and thus it's gonna accelerate much faster. So we can call this instead divide. There you go. It's not necessary. And make sure that our parameter is set. And we also want to preview our velocity before we dive into our viewport. Device velocity. And there you go. Now the only issue is that we get this bending, the curving, but when it's idle, I don't want this interpolated curving. I want it to be fully stiff. So first we want to create a float parameter called stiffness. Then back in set trail, where we interpolate the positions, we want to bring in the device velocity, but also the stiffness parameter. So in stiffness, and everything that's 0 is going to be stiff. So multiply those and bring it into the lerp. Perhaps you also want to rename this curve. So in curve stiffness. Then make sure to connect this parameter and set the standard to be 0.5. So now it's kinda curving, and as it becomes static, it's gonna be straight. And there you go. I also noticed an issue with my ribbon renderer. I think it's because I didn't use enough divisions. But this should be perfect. Look at that. Nice. So now, as it moves, the velocity increments, but will also increment when you go in reverse. So to disable that, we want to only detect velocity along a given direction. So what we want to do is take the dot product of our velocity and our system forward axis. So dot product. But we also want to invert it because, just give me a moment, because the forward is pointing in an opposite direction. And now we want to make sure that if our velocity is 0, convert all to vector. If it's 0, then take 0, and if it's not 0, then take this outcome. Now we can remap this value using a curve, so let's do that. Curve for float, and call it in curve velocity detection vector, whatever. Sample the curve using the float that we just created, and then multiply the acceleration with that value. So now it only increases or accelerates going through these conditions. So that's before we take a look, of course, set the curve, and now let's go take a look. So it's incrementing, but not in reverse. Now we still see an issue that when we go quickly in reverse, it's kind of clipping. So what we want to do is, we want, when we detect that we are reversing, slow down even faster. So let us go back to the system, and before we fix the reversing, there's actually still one more issue that has to be resolved in the acceleration. First of all, this equal check that I was doing was for safety reasons, but I came to the conclusion that it was completely unnecessary, and I couldn't just wire it up with the curve. Also, I must clamp it when it goes below 0, and we can do this by, because first of all, the dot product can go negative, and this is something we don't want. It's okay if it goes above 1, as I told before, because it will be clamped later in the end. However, it shouldn't go below 0, because this is what can happen here. So therefore, I'm clamping it. Now back to the reversing. Now let us first do a dot product of the system forward and the velocity. Now the velocity was calculated in the acceleration part, so let us first store this, and we can call this velocity between frames. There you go. Now take this value and now do the dot product. This time we don't have to invert the dot product because we are already looking in the opposite directions. Instead, now we want to again clamp it, but only when it goes below 0. Now let us do a curve sample and call this in curve reversing detection. Sample the curve. Now bring in one more parameter for the velocity slowdown duplicate and call it reversing. And this value is gonna be rather much bigger than the other one because we want to make the ribbon a lot more stiffer when it's reversing, so that it doesn't suddenly clip through the mesh. So multiply width in float in reversing slowdown and multiply this value. Now subtract, then it's being clamped again, and then velocity is set. So this should work, but make sure to again connect your parameter. Let's go back to the system. Let's take a look. Our slowdown is 0.5, so let us take a reversing slowdown of 2 maybe. That's still way too slow, so maybe 10. Oh, I remember why. It's because the curve is not set, of course. See how? So it slows down quite slow, but when I reverse, very quick. You see? Now maybe it's a bit too strong still, so let us set it back to 2 again, and this should do the trick. Still too strong. Perhaps 0.5 maybe. Oh, I see why. It's because I didn't multiply that again by the delta time. So take the delta time and voila. It's a little bit messy right now, but we can clean this up later. So it's definitely working. Let us just increase the value a little bit more by maybe 5. See? So now the next issue is that as you move the jet sideways, you see that the ribbon is not staying nicely connected to the jet, and that's because the Niagara system tick is much slower than the material tick, and so we will fix that. So let's go to the particle update, drag in dynamic material, and now say vector float, make float from vector, take the simulation position, copy this one, paste it in the second one and the third one. Now change them all so we have X, Y, and Z. Go back to your material and in a dynamic parameter, make float 3, connect them, let's call them simpos X, simpos Y, and simpos Z. Now let's take the pivot location and subtract those two positions. So now we are finding the difference between the two ticks. So we got the location in the material and in the Niagara system. If we subtract them and now add it into our world position offset, now we are refixing it to the source. You see? How cool is that? No. There's actually one issue still, and that is when you try to set the idle length to a smaller value like 1, for example, and now as the emitter moves and velocity becomes 0, then suddenly the ribbon disappears. And I don't know why this issue occurs, but I think it has to do with some type of optimization that they implemented for the ribbon renderer. However, we can fix this by first setting the idle length to a greater value like 10, which detects the ribbon renderer. And now, as velocity becomes 0, in the material we want to scale it down. So let's go to the material, and in a particle position, and subtract it from the simulation position, and multiply this with a parameter called scale down renderer fix, and then combine both results. So as scale down becomes 1, then we are offsetting it and scaling it down. So when scale down is 0, then no scale down is happening, basically. So let's go back to our Niagara system. In device velocity module, at the very end, let's drag out a map get, take device velocity, add in a lerp, convert all to float, and we want to lerp, take create a new float, and we call this one scale down renderer fix underscore strength. Again, another float in underscore scale down renderer fix strength. And now when device velocity becomes 1, then there's no scale down, 0. And if it's 0 device velocity, then read from the renderer scale down strength. And then do a map set, create a new system attribute called scale down renderer fix, and combine both pins. So I'm keeping those separate because we don't want to overwrite the strengths, if that makes sense. So compile again, grab the user parameter and connect it to the input slot. There you go. And now let's go to the ribbon renderer, scroll down to material parameter bindings, add a new slot, select both, scale down renderer fix, compile, this should be it. So you see, that's working. So now it's fully scaling down. We can set this to maybe halfway scaling down, so it will be slightly bigger. So yeah, I hope you guys found this useful tutorial. I felt like after all this years, it was about time to give back to the community, and I hope you guys can appreciate it. So yeah, if you like, then like, subscribe, whatever you want. And other than that, have a nice day. Bye.